Hello. So we are going to do a example using Newton's law of cooling this time. And Newton's law of cooling is this differential equation, which essentially is saying the rate of temperature at a certain time is equal to this stuff. And that stuff is temperature of the object after t units of time. A is essentially the surrounding temperature, the ambient temperatures of the object surrounding. K is constant of proportionality. So, with this problem, we have a cup of coffee beginning at 174 degrees, which I can actually just label as the initial condition is starting out as 174 degrees. After sitting in a room temperature of 61 degrees for 18 minutes, so that tells us the ambient temperature is 61 degrees. For 18 minutes, which I can say is going to be equal to 164 degrees. Wonderful. And what we want to know is how long it will take before the coffee reaches 148 degrees. So essentially what we want is temperature at what time is 148 degrees. Right? So given all that information, it's time to plug into our differential equation some of the stuff we know, and then of course solve it, which is the funnest part of it. So dt over d little t is equal to, we don't know the constant of proportionality yet, times t, which is a variable, minus the ambient temperature of 61. Right? And this is nice. This is just a separable equation, right? We could essentially just divide by t minus 61 and move the dt over to get, I'm going to put it over here, dt over t minus 61 being equal to k dt, and now we can just integrate, right? Integrate. It's not a terrible integration, thank goodness. And we get the natural log of the absolute value of t minus 61 being equal to kt plus a wonderful constant, right? We want to solve for capital T, so to do that, we need to get rid of that ln, and one nice way to do that is have that be the exponent to e, and then of course this essentially acts like it cancels out, and we have, I'm going to try to kind of save space here, absolute value of t minus 61 being equal to e to the kt plus c as the exponent. Now, if you remember from exponents, this is just adding two exponents, so we can actually have this base e attached to that constant, which then helps us rewrite this as the absolute value of t minus 61 being equal to e to the c times e to the kt, and this is just some constant. And actually, before that, the absolute value is really just equal to plus or minus, right? Because you could have the inside of the absolute value being positive or the inside of the absolute value being negative. So we can actually rewrite this as t minus 61 being equal to plus or minus e to the c times e to the kt. And then what I'm going to do is, because this doesn't matter what it is, it's just one big constant, right? So we can just write it as some constant. And I'm also going to add, just to skip a step maybe, plus 61 to both sides, because we do want t on both sides. So I'm going to write this as t, and I'm going to write a little t, because it's the temperature at t time, or t minutes. I think it's minutes after it's been sitting around or whatever. So t of little t being equal to some constant times e to the kt plus 61. All right, I'm going to box that just so I know that's essentially my general solution of the differential equation. One nice thing we can do now, because we have so much information above here, we know the initial condition of t of 0 being 174 degrees, so we could find our constant using that. So 174 being equal to c times e to the 0 plus 61, which gives us e to the 0 is just 1. When you subtract 61 from both sides, we just get c, and that's just going to be c equals 113. And now we have our full-blown differential, or not differential, our solution, which is 113 e to the kt plus 61, and I lied because we are still in need of k, which is the constant of proportionality. To find that, well, remember, we have more cool information. After 18 minutes, the temperature is 164 degrees. So we can use that to find k. So doing that, we will get 164 being equal to 113 e to the 18k plus 61. Then I'm just gonna rewrite this on the left side. So when I subtract 164 from both sides, I get, 61 from both sides, I get 103. Dividing both sides by 113, e to the 18k being equal to 103 over 113. Take the natural log of both sides to get rid of that e. And we have 18k being equal to the natural log of 103 over 113. And k will equal 1 over 18 times the natural log of 103 over 113. Whoa, so that was a lot. So now, instead of plugging this into our K, I'm going to leave it there and plug it in a little later, because really we want to solve for T, right? Because we want to find at what time do we get 148 degrees. So if I do that, I could solve for T as it is and then plug in the K later into like my calculator, which is what I'm going to do. So doing that, we got 148 being equal to 113 e to the kt plus 61. When we subtract 61 from both sides, we get, and I'm going to write the 113 e to the kt on the left side just because I like it that way better, being equal to 87. And I'm going to kind of try to save some space here, which gives us 113 e to the kt being equal to, I messed up there, I was trying to write something else. If I divide both sides by 113, I get e to the kt being equal to 87 over 113. Take the natural log of both sides. Natural log e to the kt being equal to the natural log 87 over 113. That kind of cancels its own self out. We get kt being equal to the natural log of 87 over 113, and t will equal 1 over k times the natural log of 87 over 113. And at this point, you probably forgot what we were even doing with all this calculation, right? Not me. So what we now can do is, first of all, we can plug in K into this, plug it into our calculator, which I have already done because I already worked out the problem. And that will give us about 50.7953, if I'm rounding to 4 decimals. I think it only, minutes, right? So just a kind of small recap. After about 51 minutes, the temperature of the coffee will be 148 degrees. I hope this was helpful.